Thank you, Professor Yaros. In the past 2 decades, we have seen a proliferation of time-of-flight cameras in the market in various settings. Most of you might have used Kinect either for recreational purposes or for research, or got your eyes tested from an ophthalmologist using an OCT. Some of these time-of-flight cameras started showing up in smartphones, and many of these cameras are an integral tool in many scientific applications. The key characteristic that distinguishes time-of-flight cameras from normal cameras is that time-of-flight cameras give information about both the intensity and also the time of travel of light. In this talk, I am going to focus on a particular kind of camera called time-gated camera that accepts photons whose total time of travel is in a path length range of interest and reject all other photons. Time-gated cameras started showing up in a lot of applications, including imaging through fog, imaging non-line of sight objects, proximity detection for cars, and for tissue monitoring. Given the large variety of applications, efficient, physically accurate rendering algorithms tailored towards time-gated cameras can be an invaluable tool for the advancement of science. For example, sensor designers are faced with a myriad of choices regarding the location of the time gate, or the size of the time gate, the width of the time gate, or the shape of the time gate. And these choices may vary from pixel to pixel, or they may vary temporally over time. Having access to efficient, physically accurate renderers for time-gated cameras can greatly enhance and simplify the process of iterating through these design choices one by one. Sensor design can be done virtually without the need to build actual sensors, which is a very expensive task, by the way. And this results in a significant acceleration and reduction in costs in both sensor and imaging system design. Additionally, rendering algorithms can help accelerate the development of computer vision algorithms that use data from time-gated cameras. For example, applications are emerging where deep learning algorithms use data from time-gated cameras to predict different scene parameters. Earlier this year, Gruber et al. Used data coming from time-gated images. Basically, they took time-gated images and made a dense depth estimation from these time-gated images. Efficient time-gated rendering algorithms can be used to generate large amount of data required to train and test these neural nets. Despite all these challenges, rendering time-gated cameras remains a challenging task. At the core of this challenge is the fact that I described earlier, the time-gated cameras only accept paths in a narrow path length range of interest and reject all other paths. When simulating these cameras, even if we consider only direct paths, right, almost all these paths generated by existing path sampling techniques will have inaccurate path length and will get rejected. And this phenomenon becomes even worse if we start considering higher bounces of light. Because of this, efficiently rendering time-gated cameras requires developing new path sampling algorithms specifically developed for this rendering task. In the rest of the talk, I will go over the path integral model for time-gated and other time-of-flight cameras to highlight both the differences and also the challenges of time-gated cameras compared to the other time-of-flight cameras. I will then describe a new path sampling strategy that is specifically tailored for time-gated rendering. I will discuss some details such as the mathematical machinery and the acceleration algorithms developed for this new path sampling strategy. And finally, I will show some applications of the renderer we built and compare with existing path sampling strategies. Let's start with the first point. Before considering the time-of-flight cameras, it is worth reviewing how we model regular intensity cameras for the purpose of Monte Carlo rendering. The intensity measured by such a camera can be expressed as a path space integral that is shown on the right top. Here, W of XE is the importance or sensitivity of the camera pixel. E of XL is the energy or the light emission term. X bar is a light path that starts from the light source and bounces one or more number of times on the scene before it reaches the camera. Here is an example of another light path, and this is another light path. Finally, f of x bar is the throughput of such light paths, accounting for reflectance, scattering, and transmission terms. As shown by Jarago et al., time-of-flight cameras can be modeled using a very similar path space integral, except for the fact that the integrand now has a path length dependent weighing function. And this term W of x bar, W of mod x bar, is different for different time-of-flight cameras. For example, a continuous wave time-of-flight camera, such as Kinect, has a path length weighing function which has a sinusoidal shape with different frequencies. A time-guided camera uses a kernel with very narrow support, corresponding to the fact that it accepts photons coming from a narrow path length range of interest and rejects all other photons. Finally, a transient camera is like an extension to time-gated camera. It captures images from not just one, but multiple shifted time gates and produces the video of light in flight. Existing path sampling algorithms developed for intensity camera will remain efficient for 2 out of these 3 time-of-flight cameras. It is worth noting that in the case of transient cameras, there has been some significant prior work developing path sampling algorithms tailored to this setting. They offer significant improvements compared to algorithms originally developed for intensity cameras. However, path sampling strategies developed for intensity cameras are very, very inefficient for time-gated cameras. And unlike the transient camera case, algorithms tailored to this case are very limited. Here is an illustration of the challenge. Most existing path sampling strategies sample light paths without any control over the path length. And almost all these paths are accepted by continuous wave and transient cameras. Because of time-gated cameras' narrow acceptance range, most of these paths do not have path lengths matching the time gate and end up being rejected. I will show you a new path sampling technique we have developed to overcome this problem. Before I do this, I want to highlight that our technique applies to any kind of camera that has a weighing term of narrow support. It doesn't have to be just a single time gate. Now let's go on to see how our path sampling algorithm works. Our procedure works in 2 steps. First, we sample a target path length by importance sampling the camera's weighing term. And then we generate paths that exactly match this path length. Our starting point for the second step is bidirectional path tracing. In standard bidirectional path tracing, we generate 2 subpaths, one starting from the light source and one starting from the sensor, and then we join the source subpath end and the sensor subpath end to create a valid light path. Because of this last step, we have no control over the path length generated by the bidirectional path tracing. To overcome this, we modify BDPT so that instead of directly joining XL and XC, we join them via a connecting vertex. Controlling the location of this connecting vertex provides us with the ability to create paths whose total path length is of desired path length that we have sampled in step 1. This translates to this equation which says that the connecting vertex, the distances of the connecting vertex from the source subpath and the sensor subpath must be equal to the path length constraint minus the source subpath length and the sensor subpath length. We identify this as the definition of an ellipsoid, which has the focal points at XL and XC, source and sensor subpath ends, and whose major axis length is equal to the leftover path length constraint. Depending on the location of this ellipsoid, we end up with 2 main scenarios. If the ellipsoid is completely contained inside a scattering volume, then we can use any point on the ellipsoid as a connecting vertex to form a complete path. Otherwise, we need to intersect the ellipsoid with the scene surfaces. Then the connecting vertex can be on any of those blue curves that are a result from the ellipsoid scene intersection. Getting this to work in practice involves a number of details which I'll briefly go over in the next part of the talk. By introducing a connecting vertex, we have changed the variables of integration in the path space integral. As a result, we need to evaluate a non-trivial Jacobian term for this integrand to have the same value. We have analytically derived this Jacobian for the case of polygonal meshes, and you can find these details in our paper. The paper also includes a few other technical details, for example, concerning the implementation of multiple importance sampling or spherical connections for direct illumination. And I won't go over these details, but I want to emphasize that through all these details, we ended up with a path sampling technique that is both unbiased and consistent. This is something we have additionally verified empirically on multiple example scenes by comparing against standard bidirectional path tracing. I also want to go back to the case of rendering surface transport. As I mentioned earlier, we need to make a geometric query intersecting the ellipsoid with the polygon to find the location of the connecting vertex. For scenes with polygonal meshes, we have developed an atomic operation that intersects the ellipsoid with a single individual polygon analytically. Given this, a naive approach to scale to an entire full scene is to iterate over one polygon at a time for the entire scene. Unfortunately, for realistic meshes containing tens of thousands of polygons, this approach is completely impractical. Therefore, it is necessary to come up with acceleration techniques for performing this new type of geometric query faster. In fact, as we show in the paper, a lot of space partitioning techniques that were earlier developed for accelerating ray mesh intersections can also be used to accelerate ellipsoid mesh intersections. In particular, once a bonding volume hierarchy of the scene has been computed, we have developed multiple tests to quickly reject a lot of polygons without explicitly intersecting them. I'm going to mention just two of them here, and we can reject all polygons contained inside a bonding box that is completely inside the ellipsoid, as well as polygons which are in the negative half space of ellipsoid's focal points. These acceleration techniques made ellipsoid mesh intersection orders of magnitude faster than the naive approach of iterating one polygon at a time. However, I also want to highlight the fact that even with this acceleration technique, this new type of geometric query remains a lot more expensive than the regular ray scene intersection. Because of this, it's important to characterize and evaluate the performance of a rendering algorithm under different camera settings. That brings us to the last part of the talk, where we show our experiments and applications. We characterize the rendering performance as a function of gate width for fixed rendering time. On the x-axis, I show the scene in both the picoseconds and also the percentage of scene size. We define the scene size as the time support of first bounce photons. At small gate widths, the proposed path sampling technique works better than standard BDPT. As the gate width increases, the advantage of sampling with path length constraint is lost. This is due to two reasons. One, almost all the paths generated by standard BDPT fall within the rendered gate width and are accepted. And two, the overhead of geometric query in ellipsoidal connections is higher than the performance we get by rendering few paths. Let's now look at experiments focusing on 4 real-world applications of time-gated cameras. All of the comparisons shown are equal time comparisons. Our first example is transient cameras that operate by imaging one time gate at a time and concatenating the time-gated renderings to create light in flight or transient video. In current cameras, the integration time for each gate width is in the order of tens of milliseconds. Therefore, if we have a scene with dynamic objects, the scene changes from one time gate to another. As a result, if we have to perform several time-gated renderings of essentially different scenes to create a transient video. Here is an example of this, where we compare transients of dynamic scene rendered with standard BDPT and our BDPT with ellipsoidal connections. We see that our algorithm results in a strong decrease in variance in the resulting renderings. Fixed time gate cameras are also used as proximity detectors for cars, for example, to avoid collisions. By imaging only photons from particular time range of interest, this creates a virtual light curtain at certain distance around the automobile. We have simulated such a scenario in a road scene using both standard BDPT and BDPT with ellipsoidal connections. If we zoom in into a couple of frames, we can see that our algorithm once again produces noticeably lower variance compared to standard BDPT. As another application, consider the case of taking a photograph through partial occluder such as fence. With a regular camera, we fully open the aperture to blur out the fence. Given that the photons from the occluder and the object of interest have different times of travel, we can use a time-gated camera tuned to get photons only from the object of interest and reject all the photons coming from the occluder. Here is an example of this, where we set our gate to match the distance of the giraffe. A lens-based steady-state camera, even with the largest aperture, would produce a low contrast image as shown in the second image. The time-gated camera addresses this. As we can see in the third and fourth figures, this is a scenario which can be simulated with much more efficiently using ellipsoidal connections. Finally, time-gated cameras have seen a lot of use in the emerging application of non-line of sight imaging. We cannot look around the corner unless the wall is very shiny or mirror-like. This is because photons scattered from the wall and the background completely overwhelm the signal coming from the object of interest around the corner. we get like couple of signal photons for every millions of background photons. This is the main reason why we cannot look around the corner. However, photons coming from the object of interest and the background photons have completely different time of travel. Therefore, we can use a time-gated camera to reject the photons coming from the background. Here I have an NLOS scene with alpha numerals S1 and 9 around the corner beyond the line of sight of camera and light source. We simulate a time-gated camera imaging around the corner with both standard BDPT and BDPT with ellipsoidal connections. And we can clearly notice that ellipsoidal connections far outweigh direct connections in rendering non-line of sight seen here. To summarize, I discussed the challenges in simulating an emerging class of time-of-flight camera called time-gated camera. These cameras are used in diverse set of scientific and industrial applications. Therefore, having efficient and physically accurate tools for them can be of great value for accelerating both sensor design and for facilitating the development of new computer vision algorithms based on data from such cameras. We have developed a new path sampling algorithm that can be used to accelerate rendering of time-gated cameras and showed experiments of several real-world applications of these cameras. Our implementation is based on Mitsuba, and we have made it publicly available at the link shown here. As time-gated cameras have received relatively less attention within the rendering community, we hope that our paper and open source implementation will encourage other researchers to look into the important rendering and imaging problem. Thank you, and please visit our poster tomorrow to learn more about the finer details. Thank you.
So we have some time for questions. If you want to step up to the mic, state your name and affiliation. Could we bring the lights up a bit? Thank you. So while we're waiting for people to come up, I was curious how much more common, or maybe what other types of applications are enabled by time-gated versus transient cameras? So you had some examples of showing transient animations, but that can be handled without ellipsoidal connections because you can deposit energy at multiple frames simultaneously. Whereas with time-gated, you have this narrow window of time that you have to generate paths for.
So you're asking regarding that dynamic scene example?
No, so I guess my question is, since I'm not familiar with the actual devices, how much more common are time-gated cameras versus transient cameras, and what type of applications do they enable that you wouldn't be able to handle with transient ones?
Brightwave Vision makes this time-gated cameras, for example, like I shown, for imaging both through fog, or like for proximity detection. You don't need a transient camera for proximity detection. You don't need to sweep through all the time gates. You just need a particular time gate. That's one application. And for non-line of sight, yes, there are applications with both transient cameras and time-gated cameras. And we don't need like the entire transient. We just can do away with time-gated cameras.
Right.
I have a question.
Yeah.
So one common strategy in rendering community to solve these kind of narrow integrant problem is just do MCMC sampling. And can you comment on the pros and cons of your technique compared to MCMC sampling?
Compare with Markov chain Monte Carlo techniques. That's the question,
or
right?
Metropolis light transport.
Yeah, Metropolis light transport and these things. So this technique can be used as a base for MLT or other techniques. Like for MLT, you need to create a light path with a path length constraint, and then you can start walking, on the curve to generate a lot more light paths which satisfy the path length constraint.
Yeah,
so
that's a
this
good
can
point.
get you, this can get additional benefit from MLT.
Yeah, cool.
Thanks.
Thanks.